So we're going to move on and look at the second part of this lesson, or this topic. And this is on page 52 of your unit handout. And there's an awful lot of memory work here. Like there's words and names and things like that that unfortunately we have to remember. And sometimes you have to remember things because you might flat out be asked, what does this mean? And sometimes you just have to remember and know definitions so you understand what questions are asking. We're going to be looking at something called the standard model of matter in terms of forces and mediating particles. Now, I've been teaching Physics 30 for a very long time, since 1989, okay? And the standard model of matter was added to the curriculum in high school only about 10 years ago, maybe a little bit longer. And at that time, I didn't do a lot of standard model of matter work in my degrees, so I thought, well, I'm going to teach this to myself. And I ordered what I would describe as the standard model of matter for dummies. There is no such book, but I did some research and I found the most elementary university physics text I could find dealing with the standard model of matter. And I am not exaggerating, I'm not lying when I tell you, I couldn't understand what was on the first page. It started off with some kind of introductory thing that says, as we all know, and then there were all these formulas. And I was lost. I didn't understand any of it. I saw that it involved some calculus. I understood what some of the stuff meant, but I couldn't get past the first page in terms of understanding. So that book, I don't know where it is. It's in a box in my basement somewhere. And over the years, I've pulled it out and I've looked at it and go, come on, give it another crack. And the left side of my brain looks at the right side of my brain and says, let's take a nap. I can't process it. It's too complicated. Why am I telling you this? To tell you that we're just touching the surface of this. Okay? We have to only be at that level. So we're going to be looking at the standard model of matter in terms of forces and what are called mediating particles. We're going to be looking at something called first generation fermions, and then developing the quark model of matter to explain different types of decay. So to begin with, the standard model of matter is maybe what some of you might refer to as, have you heard of a grand unified theory in physics? A grand unified theory is a theory that wants to bring things together. So for example, we've studied electric forces and fields and magnetic forces and fields, and yet when we talk about the four fundamental forces, we have the electromagnetic force. So somebody has come up with a unified theory that explains electricity and magnetism and called it the electromagnetic theory. A grand unified theory brings all of the forces together. And it's not complete. There's a big hole in it that we'll get to. So the reason why forces exist according to this model of matter and according to this physical theory, and it's valid. Don't think of theory as meaning something hypothetical. It's backed up by evidence. The reason is that when objects experience a force between each other, it's because there are what we call virtual particles which the two objects exchange. So when I take a pith ball that's charged negative and I bring it close to a negatively charged ebonite rod and the pith ball moves away, what this is saying is there are particles in the rod and particles in the pith ball which are continually being thrown back and forth, and that's producing the repulsive force. They're called virtual particles because they only exist for a very, very brief period of time. So here are all of the forces, and this is in your handout. You don't have to write anything down unless you want to. We know that the weakest of the forces is the gravitational, and the relative strength at nuclear distance, if we assign it 1, everything is bigger, right? What's the range? This is something you need to know, and you might remember from our previous discussion on fundamental forces. We talked about these forces to introduce the strong nuclear force. Do you remember that? That it had to be the force holding a nucleus together. The range is infinite. The hypothesized mediating particle is called a graviton. And here's the problem. It's never been observed. And if you actually go to university and study the standard model of matter, you will see the standard model of matter as explaining the three forces except for gravity. And gravity is something else. So physicists would argue that gravity is not a fundamental force. It's something else, but we don't want to talk about that here. This is high school, okay? The next stronger force is the weak nuclear force, which is, I'm going to go on a limb and say 10 to the 34 times greater. Rats. 10 to the 32 times greater. It's quite a bit larger. Of course, we know what it does. We know what gravity does, right? Do I have to say what gravity does? It pulls masses together. We know what the weak nuclear force does. It's responsible for beta decay and positron decay. It's responsible for those two types of decay. And the range is deep, deep, deep down inside of the nucleus. Certainly less than a femtometer. Less than 3/1000ths of a femtometer. And the mediating particles are called W particles, positive and negative, and Z particles. They're actually called bosons, and we'll get to that word in a bit. There are three very specific particles that are responsible for it. So when we looked at beta decay, and you can go back in your notes to convince yourself that what I'm going to tell you is true, that in beta decay, a neutron changes to a proton, an electron, and an antineutrino. That happens because inside of the nucleus, these W and Z bosons are being exchanged by other particles. We don't need to worry about the details there, okay? The next force, and by the way, we have observed this. What does that mean, we have observed it? I don't know. It's not like, oh, there goes a boson, I saw it. It's obviously some experiment where there's direct evidence of them. Are you with me on that? Okay. It turns out, and this is a wild thing, this kind of makes sense, that the electromagnetic force, which means electricity and magnetism, which act over infinite distances, which I believe is 100 times greater than the weak force, 1,000, 10,000 rats. Does your final one say 10 to the 38? It does, eh? Okay. I'm off by a factor of 100 someplace. The mediating particles for electromagnetic forces are photons, which is electromagnetic energy. So what this is saying, and don't try to wrap your head around how this works, is that when that negatively charged rod and that negative pith ball are close to each other, there are a whole bunch of photons being exchanged back and forth between those two objects, and the result is they push away from each other. The immediate question that students want to know the answer to is, what's the wavelength of the photons? And because they're virtual photons, they don't exist long enough to attach any meaning to a wavelength or an energy. They're popping in and out of existence continually. It's a bizarre idea. And again, this is why I wanted to learn more about it. And I opened that textbook and went, no, crap. I can't. I'm not capable. I'd need another degree in math just to understand the math, to understand the theory. We have observed this, directly observed it. The strong nuclear force, we know, has to be less than a femtometer, which is why the fusion of hydrogen nuclei needs to occur at 100 million degrees Celsius, so they're moving fast enough to overcome the repulsive force to get within a femtometer to fuse. And it is 100 times greater than electromagnetic forces. It turns out the particles, I love this name, they're called gluons. I love it, gluon. They're the nuclear glue that holds a nucleus together. And we have observed them indirectly. So I want to go back now and talk about this kind of grand unified theory. What they want to do, what physicists would like to do, is collapse these three main forces, because they don't believe gravity is welcome in this theory. They don't. Into one. And they already have with the weak nuclear and electromagnetic. They call it the electroweak force. So there is a way to explain electric forces, magnetic forces, and weak nuclear forces using the same set of ideas. There's a way to think of them as all the same kind of force. But this is what we need to look at. This is how it works at the high school level. Now, I don't think when we did this I talked about these other numbers, but you could also assign 1 for the strength of a strong nuclear force in the nucleus, which would mean the gravitational force is 10 to the negative 38 times the size. Do you see the scale is just backwards here? I don't think that's important. What is important is that these particles in general are called bosons. And once again, although there are physicists searching for gravitons, most physicists would say they don't exist because gravity shouldn't even be in here. I'll just throw it out there because some of you might have heard this or read this. Gravity at this level would not be considered a force. Gravity happens because a curvature of space happens. It's explained by Einstein's theory of relativity, not as a force, but as a behavior of particles moving through space that's curved, because masses indent space. I can't wrap my head around that. How do you curve this, right? Anyway, if you're interested, these are called bosons. So what the Standard Model of Matter does is explain the behavior of matter in terms of forces and everything, like ultimately chemical reactions and everything, in terms of about 300 particles. And I made a mistake here, I believe, in saying fundamental particles. A fundamental particle, everybody, is a particle that you cannot break apart into smaller particles. Okay? And I will tell you that there are, in the entire universe, we believe there are 12 fundamental particles and they're antiparticles. And everything else is composed of that. So I don't know if you remember, but at one point in Unit 2, right at the beginning, we talked about what things are made of. And we said they're made out of protons, neutrons, and electrons. And I said, kind of jokingly, if I were the cosmic chef, I would have 3 ingredients in my kitchen: protons, neutrons, and electrons. And I could manufacture anything. Steak dinner with lobster and a glass of beer, done. I just have to be able to put them together right. Turns out there's more than 3. There's 12, and they're 12 antiparticles. So you have been led to believe, I've kind of let you off the hook a bit, that protons, neutrons, and electrons are fundamental particles. And I'm telling you they're not. An electron is fundamental. If we could take an electron and put it on the table and smack it with a hammer, the biggest, fastest, most energetic hammer, you will never tear apart an electron into pieces. But you do, and we did, for protons and neutrons. So, now we're going to talk about what these fundamental particles are. All matter, everything around us that's physical, is made of what we call fermions. And you need to know this word. A fermion is a particle of matter. Specifically, fermions are the building blocks or the fundamental pieces that everything more complicated is made of. And there are 2 classifications of fermions. Fermions are either leptons or quarks. And I will tell you right now the main difference. This is going to be in your notes in a second, but quarks are fundamental particles, they're fermions, that will bond or come together with other quarks to form other particles. Leptons don't do that. Leptons are the lone wolves in our universe. If I tell you a neutrino is a lepton, a neutrino will never bond to anything else to produce a more complicated particle. A neutrino will either exist on its own or it will not be in existence. But quarks build up. They join forces to build other particles. So the 2 examples of electrons that you need to be familiar with, the 2 examples of leptons are the electron. An electron is a lepton. Now, I want to be very careful here because I just said leptons don't join forces to build bigger particles. We're not talking here, if I say, oh, an electron is in orbit around a proton, it's producing hydrogen. Hydrogen is not a particle. Hydrogen are 2 particles connected to each other. Okay? Do you understand the difference here? I think it's important that can electrons join forces with other things to produce bigger things? Yes, but those bigger things are not particles. They're just something with moving parts. There's a difference. When we talk about a neutrino in positron decay, You remember in positron decay we produce a positron, a neutrino, and whatever else, doesn't matter. Remember that? This neutrino is an electron neutrino. We haven't been calling it that, but that's what it is. When we get an antineutrino produced during beta decay, it's actually called an electron antineutrino. Okay? So you need to know about electrons and neutrinos, and we'll come back to them. Quarks, there are, and by the way, there are 6 leptons. 6 leptons. And there are 6 quarks. That's 12 particles. That's your 12 building blocks, plus their antiparticles. 24 in total. Quarks consist of up and down quarks as well as others. So there are 2 leptons of the 6 you need to know about. The electron and its neutrino. There are 2 quarks out of the 6 you need to know about. The up and down quark. Those are just words. It's not saying a quark is pointing up and a quark is pointing down. They're just words to distinguish the 2 types. So here's a table showing the leptons and the quarks. And these ones you need to know, the up and the down quark, and we'll get to the charge in a second, these are called the first generation fermions. They were the first to be hypothesized, they were first to be discovered, but then somebody came up with the idea of another generation, the second generation, which were hypothesized and discovered. So there is an electron and its neutrino that are leptons. There's also something called a muon. It's a fundamental particle. It's just this particle, that's all. And its neutrino. There's an up quark and a down quark, but there's also a charm quark and a strange quark. Those are just names, okay? They're just words to come up with a way to identify them. And the third generation, there is a tau particle, and there is a tau neutrino, and then a top and a bottom quark. So one of the things you notice is all of the leptons have negative charges other than the neutrinos. And they are -1 elementary charge. But when you look at the charges on the up and down and charm and strange and top and bottom quarks, when I say the charge is 2/3, I mean 2/3 of an elementary charge. Okay? So again, Millikan was wrong. Millikan said everything is composed of multiples of the elementary charge. That's not the case. So you were expected to know those, and you were not expected to know those. You with me on that? This is from a physics textbook, actually. So the up quark is going up. The down quark is falling. The charm quark is charming, of course. Enough said about the strange quark. The top quark has a top hat, and the bottom quark has a big butt. Okay? It's a good thing he's not taking Physics 30, because you need to know these names. You need to know what a fermion is. You need to know the 2 classes of fermions, leptons and quarks. Smug guy. Hadrons, okay. Another subset or another set of particles. All a hadron is those particles that I said quarks come together to form. So I told you leptons are lone wolves. They don't bond with anything nuclearly, but quarks do. When you get 2 or 3 quarks together, some hadrons are composed of 2 quarks, some are composed of 3 quarks. Those quark combinations can produce stable particles that are not fundamental, but they're still stable. So, and this, I don't think you need to know this, but baryons are the subclass of hadrons that have 3 quarks. And mesons are the subclass that have 2 quarks. Baryons always have 3 normal quarks or 3 antiquarks, antiparticle quarks. Mesons, strangely enough, have 1 of each without annihilating each other. Really weird. There are about 120 baryons, Two of them are protons and neutrons. So what is a proton? A proton is an up quark, and a down quark. An up quark, and a down quark. Take 2/3 plus 2/3 plus negative 1/3. You get positive 1. 2/3 plus 2/3 is 4/3. Minus the 1/3 is 3/3. You get a charge of positive 1. So that explains why, Armand, you were asking about this. That explains why an antiproton has the opposite charge, because an antiproton has an anti-up, and an anti-down quark. And all of those charges are now opposite, so the net charge is now negative 1. If you look at a neutron, I think I have it here. I want to just move ahead here. No, I don't have it here. If you look at a neutron, this would be an anti-up, an anti-down, and an anti-down for an anti-neutron. But since they add up to 0, all of the individual negatives and positives would be opposite, but they're still going to add up to 0. Do you remember that conversation? Okay. There's other baryons. There's lambda particles, omega negative particles. There's all kinds of them. And although you don't need to know all of these quarks, you could be given that information on an exam and asked, if this is the charge on a strange quark, and a lambda baryon is an up-down strange quark, what's the charge of a lambda baryon? You can figure it out. There's all kinds of mesons. Pi plus, K minus, rho positive, tons of these particles. And there are about 140. So do you remember when I said, maybe 20 minutes ago, the standard model of matter explains the behavior of about 300 particles? There are your 300, basically. 140 plus 120, plus your individual leptons and individual quarks, about 300. Maybe they've discovered more in the time that we've been talking today. I don't know. So, you're expected to be able to contrast and compare the up-down quark, the electron and electron neutrino, and their antiparticles. And this information is on your formula sheet. But before we do, it's a thing that I just got to tell you. If this is an up quark, apparently the correct terminology for the antiparticle of that is not an anti-up quark. It's an anti-up antiquark. To me, that's a double negative. To me, we're back at the regular quark. But if you see that weird, repetitive nonsense in words, that's what it means. So go to your formula sheet now. Let's take a look at our formula sheet. And on the side of the formula sheet where we have particles, it doesn't just end with alpha particle, electron, proton, neutron. It says first generation fermions. And this is not really a lot of help. We already know the charge of an electron, right? And you should know the charge of an anti-electron, which, by the way, is a positron. I've already told you the charge of a neutrino and an antineutrino is 0. What's new is that column with mass. And what's interesting is the mass is not given in kilograms. Because matter and energy are the same thing, aren't they? If you ask a nuclear physicist what the mass of an electron is, they will say 500,000 electron volts. 0.511 million electron volts. In physics 30, we kind of cut you a break and say over c squared, because that's important. And here are your two first generation quarks, their charges, and their antiquarks and their charges. And we'll get to that other column in a minute. Now, I'm going to pause there and just review this. There are fermions, which are matter. There are bosons, which are exchanged between matter to explain forces. Fermions are either leptons or quarks. Leptons include the electron neutrino, and their antiparticles. Quarks include the up and down quarks and they're antiparticles. Quarks combine to produce hadrons. What are the bosons? Oh, and those two hadrons you need to know. You need to know that. You need to know a neutron is an up, down, down. And you'll get used to that because that's the only way you can combine those charges to get nothing. Photons are the force carriers or bosons for electromagnetic force. Gluons are the strong nuclear. The W and the Z bosons are the weak nuclear. And the elusive particle for gravity is the graviton, which, again, most physicists don't believe belongs here. There it is. There's the neutron. If you look, it says neutron up, down, down. That is, up is 2/3 elementary charge. Down is -1/3. Down is -1/3. That adds to give 0. On the anti-neutron, it would be -2/3, +1/3, +1/3, still adds to give 0. Don't have to worry about spin, by the way. Something else. Okay, example 4. This is example 4 because we left off yesterday with example 3. What is the significance of me saying the mass of an electron is 0.511 million eV over the speed of light squared? Again, physicists would much rather talk about energy. This is off your formula sheet. But energy equals mc squared. And I'm being a little crafty here. I've dropped the delta. I'm not talking about delta. I'm using a different interpretation of this to mean an energy has an equivalent mass. And this is saying the mass of the electron is 0.511 million eV divided by the speed of light squared. Well, that's what mass is. Mass is energy over the speed of light squared. So we'll work out a mass in kilograms in a second, but all this is saying is if you take that energy and divide by the speed of light squared, you will get the mass of the electron. Or if you calculate the energy of the mass of an electron, you're going to get 0.511 million eV. Well, let's calculate what this is. And I'll be honest with you, because I know what happens every time I teach this. People go, why do we care? Like, what use is this? I've never seen this used on any exam ever. But it's on your formula sheet, and I think you need to know what it means. So I'm going to convert that millions of eV to joules and divide by the speed of light squared. So millions of eV means 10 to the 6. And I want to multiply by 1.6 multiplied by 10 to the negative 19 because that's how many joules there are per electron volt. So this is the energy equivalent of the mass of an electron. If I divide by the speed of light squared, I get 9.08 times 10 to the negative 31. And if I wanted to be a little deceptive, I could say, see, that's the mass of the electron, and we can move on. But that's not the mass of the electron on the formula sheet, is it? There's a multitude of reasons for it. First of all, the mass of an electron is actually 9.10938356 times 10 to the negative 31. Whenever you see brackets on something in science, it means that's what we think for those decimals, but we're not sure. It's still, the jury is still out. Okay? So first of all, the number on your formula sheet of 9.11 is not accurate anyway. And it's not exactly 0.511 either. So because of the decimals we have, depending on the resource you use, you're going to have a discrepancy. Okay? And I hope this doesn't tear your world apart that, oh my God, the electron mass is not 9.11, it's 9.1 something else. It's just because we have to use a certain number of digits. That's all it means. So if you were ever given, the only way I can see you using this idea is on an exam you're told that the mass of, we can even use something on your formula sheet. I'll pretend that it's not on your formula sheet. But I tell you the mass of a down quark is 4.8 million eV over speed of light squared on an exam. You should know what that means, and you should be able to calculate its mass in kilograms. Or I could do the same thing for a pi meson. I could tell you its mass in eV over the speed of light. Does anybody have any questions with number 4? All right. What's the only difference between an up quark U and its antiparticle, the anti-up antiquark U with a bar over it? They're oppositely charged. I feel as though I don't need an example to explain that, but formally, the charge on an up quark is positive 2/3 elementary charges. Did I get that right, by the way? I'm pretty sure I did. Yeah. And the charge, that's Q for charge, not Q for quark. The charge on an anti-up antiquark is negative 2/3 elementary charges. And now we come to the most important part of the lesson, I think. Okay? It's what this all culminates in, and it's what will definitely be asked of you on an exam. That's a picture of a proton with its 2 up quarks and a down quark, and a neutron with its 2 down and its up. And just so you know, there are different properties that quarks can have. They have something called color charge. So there are blue, green, and red quarks. And it's based on the behavior of adding primary colors together. It's really interesting, but it's a little confusing to go over, so I'm not going to. And you don't need to know it. So there's, in nuclear changes, not only is charge conserved and nucleons conserved, but color charge is conserved. That's why you will often see different colors. It's unimportant. What happens during beta decay? So we're going to be perfectly hypothetical here. What we write may not happen anywhere in the universe, but Cyrus, can you give me an element on the periodic table?
Sodium?
Sodium?
Yes, sir.
Okay, so sodium is number 11. It's not always the case that there are twice as many nucleons as there are protons. Sometimes there's more than twice as many. Sometimes there's less than twice as many. Cyrus, can you give me a reasonable number of nucleons that a sodium nucleus could have? 40? Okay. Large number of nucleons, but that's okay. This is totally hypothetical. Totally hypothetical. If this undergoes beta decay, oh boy, and did I ever make a huge blunder earlier? I don't know where it was. It might have been when we were going over some problems. But I wrote for a positron. Can't believe I did this. I wrote somewhere for a positron. I think it was when we were going over yesterday's problems. I wrote that. Does anybody remember me writing that? That's wrong. The 1 belongs on the bottom, right? It's the charge that goes on the bottom. So I don't know where that was, but I don't want to just let it stand there in case you're looking at this later. Okay? So what else is produced? A neutrino that's an antiparticle. Why? Because that's the way the world works. During beta decay, you get an antineutrino. And what else? Well, if we started off with sodium 40, we would end up with 40 for the number of nucleons up top and 12 for the number of nucleons below, which is magnesium, right? Okay. This I would describe as a beginner explanation to what's going on during beta decay. It's very, very limited. You're following some rules to predict what's going to happen. But we know that this is 11 protons and 29 neutrons. How's my math? And we get over here, so I'm switching now just temporarily to the traditional notation of things, where I don't have the two numbers, I just have the charge. We get an electron. You could use a beta particle here for the symbol. You get an antineutrino, and you get 12 protons and 28 neutrons. Are you with me on that? Okay. So the net result, when you look at this, we lose a neutron, don't we? So there's a neutron that changes into an electron plus an antineutrino plus a proton. And I would describe that as intermediate, that you're saying, okay, here's what's really happening during beta decay. A neutron transforms into an electron, an antineutrino, and a proton. But this is an up, down, down quark combination. And you know what? I'm going to rewrite that. This is an up, down, down quark combination. And there's no charge on it, but I'm showing you the individual pieces that give it no charge. And we have an electron, and we have the antineutrino, and we have the proton, which is an up, up, down quark combination. So what happens actually, now at the next level of understanding what happens is we lose a down quark and gain an up quark. Right, over here on the left we have a single up and two down. And then all of a sudden it's two up and one down. So one of these down quarks changed to an up quark. And this, I would say, I don't know about expert, but I'm going to throw it out because I'm having a hard time finding the right word here. This is a higher level understanding. By the way, the charge is conserved. If you take -1 and add positive 2/3, you get -1/3. So, you know, when I first teach beta decay, somebody eventually says, well, what's happening? Why does that happen? Where's the electron come from? And I have to explain that line at the top of the screen. And then somebody very often says, okay, but why does that happen? And now I can say, because a down quark changes into an up quark. There is a deeper understanding, and it has to do with color charge. You know, like there's a Jedi master. If there's a nuclear master, you could explain to me what's happening in terms of color charge and conservation. But you know what? That's the end of it, and you would probably still go, why does that happen? Right? So there's never an end to the why questions. There's an end to the explanation. And our explanation ends right there. So you were expected to know that that's what happens during beta decay. What happens during positron decay? Well, I'm going to pick something this time. Let's take nickel 70. What is that, 28? Positron decay, we get a positron. We get a neutrino. And we would get, in this case, 27, which is iron. and it would be 70. And again, just like the one that we made up with Cyrus's suggestion, this is hypothetical. This doesn't happen. Whether this isotope even exists or not doesn't matter. And you know, maybe what I'm suggesting to you is if you're writing an exam and the question is what happens during positron decay, make up something and do the positron decay to find out. I'm not going to provide as much detail in the explanation here. I'm going to tell you that you should be able to look at this and say that the following change occurs. And I do have a mistake on the board. What is it, Sasha?
You made it an antineutrino.
Right. I don't want an antineutrino. I only want a neutrino. I think it's reasonable that looking at the numbers of protons to begin with and afterwards, you see that a proton changes to a neutron. I think it's also reasonable for you just to look at the fact that this is up, up, down, and this is up, down, down, for you to say that the true change is an up quark changes to a down quark. So we don't need all of those extra pieces. Here is the net change. And again, if you were to check out the charge, charge is conserved. I'm going to end it there. I could do the same thing with electron capture. You know, you figured out during electron capture what happens. I believe it's a proton plus an electron changes to a neutron and a neutrino. You could figure out the quark transformation there as well. So there's, again, we can go deeper and deeper, but I will tell you this. There's nothing deeper than quarks. We don't believe, you know, there might be some holdouts in the physics world who believe that one day we'll smash a quark into smaller pieces. We're back to the questions that we answered earlier in the week, which is these things were discovered because we were looking for them because we needed them to make the theory work. There is no reason why we need smaller particles. Quarks completes everything. Most things, I guess. Never say never, right? Who knows? It's like Horton hears a who. How many of you know what I'm talking about, okay? Well, maybe at the very end, there's a deeper whoville. There are some questions related to all this, not only for you to know how to answer, but to get you thinking about this kind of stuff. And that is the end of this lesson, and that is the end of the unit, and that is the end of the course, except for a lot of review.